So far, we've talked about how a line can intersect a plane and how a line could be parallel or distinct to a plane. But today we're going to be looking at how two planes could intersect. So when I look at the three cases that you can see right now, our first case is when the two planes intersect. And if you look at this picture, it looks like the two planes are cutting through each other. When they intersect, there's not just going to be a single point of intersection, it will be a line. So the intersection will be a line. Case number 2, the two planes are parallel. And case number 3, the two planes are right on top of each other. They're the exact same or they're coincident. In the past, what I've found that students don't have difficulty with is visualizing these three cases and understanding the differences between these three cases. With that being said, I have found that students do have a more difficult time providing written solutions for cases like these. So in the next little bit, we are going to go through a couple of examples. So you're going to see what solutions look like, and we'll go through a couple of them together. So our first example says, describe how each pair of planes intersect. So again, when I'm describing a plane, I'm going to use the pi symbol. So plane 1, its scalar equation is 5x plus y minus 2z equals 2. And plane 2, 5x plus y minus 2z equals negative 8. So the first thing that I notice right away is that the normals for both of these planes are the same. So for my first normal, I'm going to take a look at these coefficients, and I get 5, 1, negative 2. It's going to be the exact same for plane 2. Now, since both of these planes have identical normals, I know that I have two options. Either these planes, so first of all, they're parallel. So either they're going to be parallel and distinct, or they're going to be coincident. There is a quick test. If I take a point that's on one of the planes and I test that in the other plane and it's on that plane as well, then that means that they're coincident and all other points on that plane would be on the second one. So to test this theory, I'm going to pick a point, any point that's on plane 1, and then I'm going to plug that in and do a left side, right side check for plane 2. So just to make my life a little bit easy, I chose a point 0, 0, negative 1. So this point satisfies the equation for plane 1. And I'm going to go ahead and I'm going to plug that in to the left side and the right side for plane 2. So I have that set up right here. So I'm going to get 5 times my x was 0 plus my y was 0 minus 2 times my z was negative 1. So this is going to equal 2. My right side is negative 8. So right now we know that left side does not equal right side. So since we discovered that this point was on plane 1, but it wasn't on plane 2, we know that these planes are parallel and distinct, which means there's going to be no intersection at all. All right, example 2. So again, I have the equation for plane 1 and plane 2. Again, it's a scalar equation, and so I'm going to go ahead and I'm going to write my normals. So I've got my normal 1, 7, 3, negative 4, and my normal 2, 14, 6, negative 8. Now, what I notice right away is that these normals are scalar multiples of each other. So 2 times the first normal would give me the second normal. So since these are scalar multiples of each other, we know that these normals are parallel to each other, which means that our original planes are also parallel. So again, we only have to think about two possibilities here. Our planes are either parallel and distinct, so no solutions, or they are coinciding, so an infinite amount of solutions. I'm going to follow the exact same steps that I did on the last question. So I'm going to pick a point on plane 1, and I'm going to check if it's also on plane 2. So I just chose a point 0, 3, 0, mostly because I know 3 times 3 is 9, and I don't want to deal with fractions. And I'm going to do a left side, right side check. So I've got 14 times 0 plus 6 times 3 minus 8 times 0. That's going to give me 18. So I have figured out that left side is equal to right side. So since this point was on plane 1 and plane 2, I do know that these two planes are parallel and coinciding. So one quick thing that I did want to mention, if I were to look at my two original equations, I can see that the second equation, or the equation for plane 2, is just plane 1 multiplied by 2. So I could have used that right from the get-go, and I could have said, automatically I know that these two planes are identical, and I wouldn't have had to do all of this work. But these steps will work for both cases, so it is a good habit to show, and I think it does help kind of explain that for everyone else, which is why I chose to do it instead of just saying right from the beginning, okay, I know that these are coincident and intersect everywhere. But you can use that if you would like. So the third part of example 1 still, I have two more planes, two more equations. So the first thing that I'm going to do is find my normals. So normal 1, 2, negative 1, 1, normal 2, 1, 1, 1. These are not scalar multiples of each other. They're not parallel. So I know that these two planes are not parallel, and so the only option that I have is that they intersect. Now we know that two planes intersect in a line, so I need to now figure out the equation of that line. When I'm trying to solve for this equation, I have a major problem. I have two equations and three unknowns. You know by now, or you should know by now, that we can't solve something like that. You will learn ways to do this in university, but right now we're going to have to think back to what we know. So if you think back to grade 10 and you use elimination, we can easily eliminate at least one of these variables. So I'm going to choose to eliminate my z's just because they're both a plus z, but you could just as easily eliminate the y's. So because I'm going to be eliminating these z's, I am going to subtract equation 2 from equation 1. So I have 2x take away x, and then a negative y take away another y, so that's a minus 2y, z take away z, we know that that's going to result in nothing, and then negative 1 take away negative 6, so a plus 5. Now that I have this equation, what I need to do is I need to assign a variable, any one of these variables, a parameter, and I'm just going to pick t. So I say here that I'm going to let y equal t, and if I do that, I'm able to rearrange this equation and get x is equal to a positive 2t subtract 5. So I've taken these two terms, I've moved them to the other side of the equal sign, and again, I let y equal t. So far we have a couple of things going on. Maybe I'll just use red here. I've got one equation, so I have let y equal t. I just found x in terms of t, and I'm going to take these two pieces of information and I'm going to plug that into my equation for plane 2. It doesn't matter which equation I use, but I'm going to go ahead and I'm going to say that x plus y plus z minus 6 equals 0. If I plug these equations in, I have 2t subtract 5 plus my y was t plus z minus 6 equals 0. I have a 2t plus a t. That's going to give me 3t. I have a minus 5 and a minus 6. That's going to give me minus 11 plus z equals 0. And so when I rearrange this, I have z is equal to 3t plus 11. And I wrote it, but I didn't say it. That should say z is equal to negative 3t plus 11. Sorry about that. So to finish off this problem, I'm just going to rewrite this. So I had x was equal to 2t minus 5, y was equal to t, and z is equal to negative 3t plus 11. Since I have these three equations, I am able to write my solution, or the equation of the line, more specifically the vector equation of that line. So the intersection of plane 1 and plane 2 is a line. We already talked about that. And the equation of the line is going to be found by using the three equations that I just wrote down here. So I'm going to pull out my direction vector. So the point that goes in front of the t. So I have a 2, 1, -3, and then the other points are going to be used as the point that helps define the line. So -5, 0, 11. We are not going to spend too much time on the next little section of the course. So this is, we're going to be talking about the intersection of three planes and what could potentially happen. When you go to university, you won't really talk about it at all in calculus, but if you're taking linear algebra 1, you'll definitely go through it in detail and you'll learn some very efficient ways to solve these, more particularly involving matrices. So we're just going to go through it very briefly. Again, it is part of this course, but we're not going to spend a lot of time on it, and I'm not really going to ask you very much about them. So to start this off, we're going to be talking about consistent systems. So a system of three planes is consistent if it has one or more solutions. So I'm going to be putting up the three possibilities for this case. So for three planes to have a solution, there's going to be three possibilities. And then we can talk about what happens if something is not consistent, if there's no solution. Okay, so I have some diagrams here. The three cases, if we have three planes intersecting in a consistent way, so meaning there's one or more solutions. So case number 1, the three planes, as you can see, are intersecting in a way that they only meet, all three of them only meet at one specific point. Case number 2, these planes are intersecting in a way that they are meeting in a line. So I'm going to try and just draw this in red here so you can see. So there's going to be infinitely many solutions, and we'd be able to find the equation of that line, very similar to what we did in the last part of the example. And then case number 3, this just looks like a single plane, but really it's because there's three planes that are identical all on top of each other. So plane 1 is equal to plane 2 is equal to plane 3. And again, there's infinitely many solutions because all three planes are the exact same. So on this slide, we're going to be talking about what happens if there is no solution. So if we have three planes that have no solution, we're going to say that it is inconsistent. So we have three cases here. Case number 1, all three planes are parallel and distinct. So that means obviously there's going to be no solution. Technically, there is another case here where if two planes were coincident with each other but parallel to the third, there would still be no solution. Case number 2, we have two planes that are parallel with the third plane crossing through that. So when I look at this diagram here, I do have solutions just between two planes, but I have no solution for all three of the planes. So all three of these planes never intersect at all. And then case number 3, very similar to case number 2, I have two planes intersecting multiple times. So there's an intersection here, here, and here. And so I could get a solution between two planes, but again, there is no point or line or anywhere where all three of these planes intersect at the same time.